Good morning, everybody, and warmly welcome to this parallel session number 2, which is about soil carbon monitoring, reporting, verification, scientific basis for public and private incentives. My name is Jari Liski, and I will be the chair of this parallel session this morning, and also the session on comments of the same theme in the afternoon, and that will also be in this same room. So I'm from the Finnish Meteorological Institute. I work there as a chief scientist, and then I also have a research group at the FMI studying especially how to verify, monitor and report carbon and greenhouse gas balances of agricultural fields. So I'm also personally very interested in this topic and the themes. I'm very much looking forward to the presentations and also the questions and discussions that we will have. So once again, warmly welcome to this session. And whilst the morning consists of 4 keynote talks, we will have first Pete Smith giving the presentation remotely. Then we will have Jagadeesh Yeluripati giving the presentation here at site. And then we will have a recorded video from Jean-François Soussana. And then the 4th presentation will be given by Istem Fer here at site. So this is the program for this morning before lunch. Yes, and perhaps I do not need to introduce the importance of this monitoring, reporting and verification that has been mentioned several times in our parallel sessions this morning and also yesterday. So whatever kind of incentives we're developing, what kind of regulation we're developing, any kind of steering mechanisms to enhance soil carbon sequestration, we need reliable monitoring, reporting and verification methodology. So I don't think that we need motivation any other than that for this theme this morning and then in the afternoon. Yeah, so now I'm really happy to welcome the first speaker, Professor Pete Smith, who's a chair in plant and soil sciences at the University of Aberdeen, to give the first keynote speech. So I'm sure most of you, if not all, know Pete. Pete has done an enormous amount of work in this field and is certainly one of the most well-known scientists in this field in the whole world. So we are very happy and honored to have Pete giving the first of these keynote talks. And so welcome, Pete.
Thank you very much, Jari.
I'll just, because I've been in a similar situation as you are, so you're giving the talk remotely, I'll tell you a little bit about this conference. So we've had the parallel sessions, the plenary sessions yesterday, and we had about 300 participants here at site, and we had about 300 also following the events online. And we are here situated on the seaside of Helsinki, so you visited Helsinki, so you know what I'm talking about. It's May and the sun is shining, so the landscape's beautiful. And now we're having like 3 parallel sessions going on, and I'm happy to see that almost all of the seats in this room are reserved. We have about, about 60 or maybe even 70 people following at site. And then I heard that we have something like around 150 online participants. So this is the kind of to set the scene a bit to you. And then we are running now a little bit late on the session, but so we will start the lunch a little bit later. And but otherwise, I need to be quite strict on the schedule so that we will have enough time for everybody. But Pete, now we are looking forward to hearing your 20 minutes presentation, and after that there's a 10-minute slot for questions. So once again, warmly welcome, Pete, and the floor is yours.
Thank you very much, Jari. Can you see my slides? Are they available?
Yeah, the slides are there on the screen, and we see your video of yourself next to that. And it's excellent audio, and the visibility is great, so everything's fine. Go ahead, Pete.
Okay, right. So this morning I'm going to talk about what an MRV system for soil carbon might look like. So the most obvious thing, of course, is to directly measure the soil carbon. So this usually requires soil sampling, field sampling and lab analysis. This is the gold standard in terms of accuracy. You can use combustion analyzers, CNN analyzers, but it requires destructive field sampling. extensive sample preparation, laboratory analysis, and it's slow, costly, and labor intensive. So whilst it's the gold standard, whilst we use it in scientific research, this can't really be used as something that every farmer is going to do on every field. The challenge being that changes in soil carbon are quite slow, and changes are quite small relative to the large background. So we need to find a way that is cost effective and also accurate. So in addition to the direct combustion analysis, there are other methods that have been proposed, such as ground-based in situ carbon sensing. So these are things like near-infrared spectroscopy, Raman spectroscopy, and such like, where you take a spectrum of the soil, and from that you try and isolate the peaks of the soil organic carbon or soil organic matter, and from that you can infer a concentration. So that offers potential for rapid, high-resolution mapping of soil organic carbon. But the challenges at the moment are, for it to be accurate, the general calibration of these systems. There's an effect of varying moisture, for example, and soil mineralogy affect the signal that you get. And it can also be fairly high cost in terms of maintenance of the sensors. The sensors are quite expensive currently, and the maintenance of the sensors can be quite tricky to maintain them. But the largest problem at the moment is that we just don't have the accuracy yet. We're still working on it. Obviously, we don't have the accuracy yet for detecting changes in soil carbon. It's good for mapping the carbon content around the field, but it's not good for detecting changes in soil carbon, these small changes against a large background. And there are other direct measurement, the other approaches that can be used are things like satellite-based carbon sensing. I first heard about this about 20 years ago, and it was said to be a promising technology. And as I understand it, it's still a promising technology. So it might continue to be a promising technology, but never actually deliver. But if it does, it can get, it's inexpensive, it can give global coverage. But generally it needs bare soil, so it's best on fallowed cropland. And if you're looking at other types of land use or other periods in the season, then it's difficult to get a measurement, and it's also difficult to get anything more than the very top layer of soils. And it's not suitable for vegetation and residue cover. For example, where you've got soil conservation practices, it's not suitable for directly sensing the soil carbon, but it's good for large area surveys and for mapping. So it does have a role, but in terms of direct measurement for verification, I think there's still a long way to go. On the point of the handheld devices, the other methods that where you don't have to use direct combustion. There are these methods. There's a company called Yardstick in the US have got quite a lot of startup funding and funding from the US government, which is a handheld device that uses spectroscopy, and you drill lots of holes in the ground using a standard drill, DIY drill that you can buy in hardware stores. It drills into the ground, and you've got a sensor in the tip, and it feeds up and reads the soil carbon. And at the moment, I was speaking to the developers of this. At the moment, it's good enough to measure soil carbon, but again, it's not yet accurate enough. There's about an order of magnitude improvement in accuracy and in precision that's needed to be able to measure changes in soil carbon that may occur from changes in land management. But this is a really promising technology, and what you lack in accuracy, you gain in the fact the number of samples you can take, because it's very quick and easy to take hundreds or even thousands of samples in the same soil. There are other techniques such as machinery mounted devices that use, for example, gamma radiation from soils. And whilst they don't directly measure soil carbon, we can think about getting soil carbon PIDA transfer functions that are related to some of the parameters that these gamma radiation sensors can measure. So again, it's promising, but at the moment we're not quite yet there for soil carbon verification and monitoring. So if we can't use direct measurements and we can't use proxies of direct measurements, how can we pull together the information that we've got to try and get closer to an MRV system? We need fewer high quality direct measurements. So we're still going to need direct measurements. So at project scale, these are the sort of things we can do. So we need to take less measurements, but some direct measurements so that we have a calibration and something to compare against. We need to reduce uncertainty, which from this we can use locally scaled predictive models, which are being calibrated using local data. And we need the capability to easily incorporate farm level activity data. So this is a scheme that we came up with that we published in Global Change Biology in 2020. And I'm going to go through this in a little more detail, each one of these components. But it includes components that we have access to. So there are long-term experiments, which we have. We have short-term experiments at various sites around the world. We have soil organic matter or greenhouse gas models. We have spatial data to drive those models. We have the activity data that's collected by farmers. We have in various places in the world soil spatial resampling surveys on grids across different countries. And of course, we have ever increasing capability for remote sensing. I'm going to go through each of these in a bit more detail, but all of these can be combined. So whilst we have the components, each of these components are available, we've not yet combined them into an effective monitoring, reporting and verification system. At the same time as we published this paper, in America, Keith Paustian was also developing a paper about soil MRV, and he came up with a very similar system because basically it's an idea that time has come, and you can see a lot of the same components. I must say Keith has put together a much nicer graphic than the one we came up with, but it's basically doing the same thing. It's got activity data from the land manager, it's got models, it's got data, it's got remote sensing, it's got activity data sets. So this is the same idea. It was published in a separate paper. We didn't know about each other's work, but it's an exercise in convergent thinking. We came up with more or less the same ideas about a system that could be used. So I've used some of Keith's slides in the presentation with his permission because we have similar thinking about these issues. So let's go through the diagram in a bit more detail to say what we've got. So the first one is the long-term experiments at benchmark sites. So this is where you take samples at different times, maybe over decades or maybe over even longer periods. You have different treatments and you measure the soil organic carbon over many decades, or you can even have chronosequences which have different management practices implemented at different times in the landscape, which you use as a proxy for time. So when we looked at this back in 2012, we were looking at what sort of data sets we have available. So in our 2012 paper, we looked at, this was the distribution of land use experiments evaluating impact of soil organic carbon stocks. So this is shown in panel A. In panel B, this was the distribution of tillage experiments evaluating the change in soil organic carbon stocks, and you can see compared to the land use change experiments, we got much better coverage, but not so many experiments in the tropics and subtropics, but quite a few in North America, South America, Europe, and Asia and Australasia. And if you look in panel C at the bottom, these are experiments evaluating different agronomic practices, and again, even more experiments around the world. So we have quite a global network of long-term experiments which we can use to benchmark our models and which we can use as a benchmark for a global MRV system. Again, more experiments needed in the tropics and subtropics, but we do have some experiments at least, and we have quite good global coverage. So these experiments were around in the something that we started up in the mid 1990s called SOMNet, the Soil Organic Matter Network. That's no longer active. We handed over the data to the long-term Soil Experiments Network. Again, that's no longer active, but all this data is archived and is just waiting to be used. So we have these long-term experiments, we have that component of the MRV system, we just have to utilize it. So how can we complement those long-term experiments with shorter-term experiments? And we know we already have these. Some of them are nested at long-term sites. So where we got the long-term measurements going on, we also have, for example, flux towers. And these measure the shorter-term fluxes of things like methane and nitrous oxide, which can complement our measurements of soil organic carbon, or even CO2, which can complement our measurements of soil organic carbon, and can help us investigate the processes and develop novel tools and calibrate our models. And there are numerous examples of this. For example, eddy covariance towers. There are hundreds of these just over the UK now. So we have many thousands over the world. And this is the distribution as of 2012. And the distribution, if I were to plot this and to get this data again, we would find that there were many, many more flux towers available, providing data up into the FluxNet site. So we can access this and we can use them to ground truth our models, and also to get direct estimates of greenhouse gas fluxes from different management practices around the world. So we also have these flux towers, but again, we haven't integrated them with our long-term data into a system that could be used for MRV. But that data is just waiting there to be exploited. In terms of the models, I've spoken about models a bit already in terms of calibrating models using the data. But we have these, we have many soil organic carbon models and greenhouse gas emission models, which have been developed on long-term and short-term data. We can evaluate them against long-term data, short-term data. We can apply them directly, or we can derive emission factors from them to apply in a tier 2 methodology. So just an example, we have the representation of soils in models. We've got simple models like statistical regressions. We've got numerous soil models, YASO, which Jari developed in the room with you there. There's Rothsea, ECOS, and there are broader ecosystem models like Daycent, Century, DNDC, and many others, which can be used to represent soil carbon changes. We can develop and test these models using short-term data. As I mentioned, we've got the long-term data and the short-term data. Things like the long-term data I've already mentioned. We got isotope natural abundance data, we got flux data, respiration data, and isotope pulse labeling data. All these things can be used to develop and calibrate models, and we can test them then against long-term experiments. And this example shown here was a comparison that we did back in 1995, believe it or not, going back years and years, comparing 9 soil organic matter models to see which ones work best. And when we've got that evaluation, when we work out which ones are working well and which ones aren't, we can improve the models, and then we can go through this whole process again. So further developing the models, calibrating them, improving them, and then testing them on independent data. So we have a plethora of models which we can use in an MRV system, and some of these are being used already. And I think Jean-François, Istem, and Jagadeesh will talk about some great examples that we've got in Europe for doing that. Just example, this is the soil CNN routines of the ECOS model. Just to give an example of what these models look like. Pools, the carbon's broken down into conceptual pools. This is for carbon on the left and nitrogen on the right. And they use meteorological data, management data, and soil data, and other environmental data to simulate changes in soil organic matter and soil carbon. And this is Daycent, this is the Century schematic, which is showing a similar system, different pools, different conceptualization, but the same sort of idea with different pools of conceptual pools of organic carbon. And the DNDC model similarly. So we have a bunch of these models that we can use which all can be used in various ways within an MRV system. So to run the models, we need the spatial data to drive them. If we're going to run them in tier 3 mode, that's to use them all across the landscape. We need data on climate, soils and land cover. In 2012, we did an assessment, a sort of an inventory of what sort of data was available to run the models. So the soil data, we already had a bunch of data available in 2012. We now have the Harmonized World Soil Database. We have things like soil grids, and we have other national systems which are getting down to really fine spatial resolution, a few hundred meters. So we can use that soil mapping and those soil data to drive the models, to initialize the models. And we also have land cover data and land management data, which is becoming ever more sophisticated. This is going back to 2012, and this is looking at the products that are available then. But we now have the land use harmonization project, the HIDE data and other data sets, which are really fantastic products, which give you global land cover. So these are just two examples of the sort of spatial data sets where we've got global coverage, which we can use to drive the models. The most tricky thing often to get, even if we've got great models which are really well calibrated, is we just don't know the management data on the farm to drive the models. And if we don't know the management data, we can't accurately predict the soil carbon, the changes in soil carbon, or even to assess what we're trying to estimate about the management activity on the changes in soil carbon levels. So the best way to get this data is to try and link into what the farmer is already collecting. So the farmer already collects a bunch of important information. So operations on the field, when they till, how deeply they till, when they fertilize, what fertilizer they use, how much fertilizer they use. So all this sort of information in many countries is collected routinely, and it's often available spatially from National Statistics Agency, who collect farmer returns. So the best way that we can collect this activity data is to use the data that's collected by the farmers and put in as part of their claim for example, single farm payment under the Common Agricultural Policy. So the sort of information that they already collect, if we can access and use that data, we can use these to drive the models, to give the models the important management information that drive the changes in soil carbon that we can use in the models in the MRV system. So it's important that we can get a link to this activity data. Otherwise, we're having to guess. In number 6 is remote sensing. So we can use this to verify activity data. We can use it as input to run the models, and it can give us information about soils and vegetation. So some examples of this are remote sensing of management activity data. So we've got optical sensors and radar sensors, multispectral and hyperspectral satellite data, which can tell us if there's tillage and residue coverage. It can assess the surface roughness, and it can also, if we get multispectral, it can also give us the crop cover, the crop type, and the crop cover presence. And we can also detect flooding from remotely sensed data. So we can use all this sort of information either to feed into the models, or with a data assimilation approach, we can even assimilate this data in near real time. And Jagadeesh is going to be talking after me about a near real time MRV system that he's led the development of in Scotland. And on the other side, we have productivity surrogates for model data assimilation. For example, leaf area index, canopy N, gross photosynthesis. All these can be assessed from remotely sensed products, and we can use these to feed in to get updates to the model in terms of NPP and growth and plant growth, which then, of course, is a surrogate for carbon inputs to the soil. So again, much data out there from remote sensing and earth observation, which we're not yet exploiting fully in MRV systems. And the last thing is spatial soil resampling using a survey grid. Many national surveys have these resampling schemes which go back every 10 or 20 years and measure soil carbon at the same points and can map this over time. A good example was published in Nature from the UK by Pat Bellamy et al. And her colleagues, looking at changes in carbon over a 20-year period, 25-year period, and mapping those carbon changes out and trying to allocate those to different changes in land management, in climate, and all those sorts of things. So this data, this other spatial data, is very useful as a calibration or in a verification data set, which we could use in an MRV system to check that we're getting it right. So that sort of system is the gold standard. I think this is something that we could work towards, and these sort of systems are in development around the world. I don't know of any that are actually fully operational yet, but we'll be hearing a bit more from Jagadeesh, from Istem, and from Jean-François via recording in this session. But the FAO has got ahead of the game, and it's developed this system as REC Soil, Recarbonisation of Soil Programme, which has a bunch of data that's been put together globally. And the idea of this is to generate a global soil organic carbon sequestration potential map, which can then be used by countries. They can develop their own estimates of soil carbon sequestration. So mainly developing countries which have more limited capacity to do this sort of work. This is a possibility for them to develop their own systems to encourage recarbonisation of soils. So I'd encourage you to go and look about what's going on here, the information that's coming in, the countries that have already submitted data. This is a fantastic initiative coordinated by FAO, which is just starting to deliver results now. So in summary, I think one of the biggest barriers to implementation of soil organic carbon as a mitigation measure is the challenge of MRV, monitoring, reporting and verification. I'd argue that all components of an MRV framework exist to some extent, but they're uneven globally, as I showed earlier, the long-term experiments that are missing in the tropics and subtropics, and they're not integrated. FAO's REC Soil Programme is an opportunity to bring these together, especially in developing countries, and that's starting to happen. But I think all countries of the world, either internationally or nationally, could start to pull together their resources to try and develop an MRV system that can be used. There are some great examples in this session. I've seen the speakers and I've seen what they're going to say, so stay tuned. There's some great examples. I'm going to try and watch some of those on the live stream. And there are some new non-destructive measurement techniques that are in development. We need to watch and see how these develop and monitor how they progress. I think there's some really promising developments, especially with the handheld devices, which aren't quite there yet. But as we put in more investment, as we get better, and as we provide more information, more spectral libraries to calibrate these against, then we may be able to get them to a stage where we can directly measure changes in soil carbon. I'd lastly say that there are great opportunities for robotics, AI, machine learning, data assimilation and advanced modelling. So for the nerds of you out there, as I am, I think there are some great opportunities for new developments in AI and machine learning and all these other up and coming techniques that we could use to help us improve soil MRV systems. So I'll leave it there, and if there's any time left, I'll take any questions before we move on to the break in the session. Thank you very much.
Thank you, Pete. What a fantastic kind of introduction to this round. I'm sure there are many people here listening who are developing components of the system or looking for the overall thing, doing the modeling. I think there's so much for everybody. So this was really an excellent presentation to help us to set the scene for the rest of the day, and also including those who are interested in how far we are for delivering the information for the stakeholders. So I mean, that all was there. That was exactly like what we were looking for. So thank you so much. Yeah, indeed, we have 5 minutes for questions now, and there's one hand up over there, and there's Nicholas. Can you see that? And please say your name and the institute you're coming from. Is that right?
Hello. Hi, Peter. It's Glenn here. I'm sorry you couldn't make it to this conference. Hoping to meet you in person and maybe another day. I'm from Carbon Farm Hubs. Very interested in what you're doing. One thing that sort of like surprises me, which is a key part of this conversation, is the microbiome. I know you're very aware of the microbiome and its importance in actually the carbon sequestration, but there seems to be a big lack of understanding, measuring and verifying the soil succession and alignment to the crop succession. Is there anything in development in that area? Thank you.
To my knowledge, there isn't. Most of the, I think we've got a big enough problem with just monitoring and verifying soil organic carbon stocks, bulk soil organic carbon. So I'd really like to do more work. I'd really like to understand the contribution. I think it's at this is more at the cutting edge science side of things rather than the operational side of things. When we understand more about the science, we can start to think about how we integrate that into MRV systems. But I think that's a sort of a that we have to run before we can walk. We have to walk before we can run, rather. and I think that's running, and we can't even walk yet.
Okay, thanks. Any other questions? Yeah, it seems that there are not any more questions from the audience, Pete. So yeah, thank you once again for joining us and giving this excellent presentation. So thank you very much, Pete.
Thank you very much. I'll join you online. Bye.
Yeah, that's great to hear. Bye. Yeah, and then we move on, and what we will hear next is kind of 3 examples of different monitoring, reporting, and verification systems. Like Pete already mentioned, we will start from Jagadeesh Yeluripati. I hope that's acceptable at least. So he's a senior scientist at the James Hutton Institute in Scotland, and he will give a presentation entitled Near Real-Time Greenhouse Gas and Soil Carbon Change Predictions, a Step Towards Net Zero. So, Jagadeesh, the floor is yours, please. Sure. And one thing that I would like to mention, that now we have 15 minutes for the presentation, and then we have 5 minutes for the questions. So.
Sure.
Yeah,
I'll try my best. Good morning, everyone. I think it's great that Pete already spoke about the need for a credible MRV and integration of different aspects of it, different elements of it into the MRV. So here, actually, I'm going to show you today conceptual framework of MRV that in future can incorporate all the elements which we are discussing, including biodiversity and others, and also first functional prototype of MRV, which we came up with. So in order to do that, I just give a few slides of a bit of warm-up, what is the concept, and also what is the need for MRV, what elements it should cover, and then really go into what we have produced into this. Yeah, as we all know, greenhouse gas emissions from EU from different countries in 2019. If you look at the sectoral wise, in more or less in all the countries, 10% of greenhouse gas emissions come from agriculture. And there is a lot of effort was put in last few decades. There is substantial reductions in greenhouse gas emissions in energy sector and transportation sector. But if you look at any country, more or less, the agricultural emissions have stayed the same or in fact increased. But agriculture, as we all know, offer a huge opportunity, not only reduce the greenhouse gas emissions, but also sequester the carbon, because it's highly managed ecosystem. It's one way we can even sequester more into this. It's a recent IPCC report. You might have seen this one. Even though there are several efforts were put in place across the world to reduce the greenhouse gas emissions, the overall emissions were in fact increasing. Even the last decade is the highest emissions that produced. So we need to do a lot. If you want to do reach the net zero, all the sectors has to contribute in order to achieve net zero. So agriculture must do its own. So, and also agriculture offer a unique opportunity here because other sector, if we invest in energy sector, transportation sector, it will only reduce the emissions, whereas the agriculture sector provide the resilience and food security. There's a lot of added value to this once we put in effort. So, and also this report very clearly states that digital technologies can play a crucial role in mitigating the greenhouse gas emissions and increasing the sequestration. So that's what our effort is, how we can bring different digital technologies together to create an MRV. So just to give a background, this is all, we all agree, already from yesterday we have discussed this one. Technical potential of carbon sequestration in soil is very significant. We have overall consensus on this in the scientific community. So croplands worldwide could sequester between 0.9 to 1.8 petagrams of carbon, which is huge potential to tap into. But what is the challenge we have is that soil organic carbon content in greenhouse gas emission cannot be easily measured, which is a key barrier for implementing programs for net zero. So this is one of the challenges. That's what we need MRV for operationalize. But there is a need for a credible and reliable MRV platform, not only for financial markets and operations, but also for the national reporting. Because the way current reporting is done, the methods used in the national scale estimations were quite different from the methods used in the farm level. So as we go towards the 2050 or the net zero, we are going to have a conflict between this. There is a need for harmonization of these methods. Otherwise, we tell some place that we are net zero, some methods we say, no, at the farm level, we are not net zero. So this conflict we need to avoid. That means we need a more harmonized methods and centralized methods, in my view. So that is what one of the heart of this MRV, what formulation we have done. So, oh, sorry, it went back. Oh, sorry, it's sorry for that. Can I go back?
There's a smaller button below the big button.
Oh yeah. So why we need MRV? One is for national reporting and also for the emission trading. One of the barriers MRV we need is that currently the emission trading market is really stuck because of lack of credible MRV. And we need to track towards the net zero. The farmers need to know what management practice they're practicing now that will lead them to net zero by 2050, or close to it, at least. So they are in the right direction. So we need to offer all these elements into this. But any MRV, there are certain elements we need to fulfill. One is we need to demonstrate the permanence of the carbon, which is very central to any MRV. And also the additionality. These are another criteria. The other one is leakages and complete traceability of the carbon. These are the 4 elements which are extremely crucial and central to any MRV, credible MRV. So that is the basis for our framework. When we designing this one, we know that these are the 4 elements. If we design without this, there is no point in doing something out of this. So the next part is how the project actually we designed. The idea is to produce create an iterative near real-time digital MRV system that will allow dynamic model forecasting at crop level, greenhouse gas emission, and net carbon sequestration at the farm level. If we look at the current MRV landscape, they fundamentally look at 2 aspects of it. One is either they follow the modeling approach, which is cheap in many ways, or they go for a very strict monitoring approach. That means either measure the carbon, and again, after a few years, they measure the carbon. But both have both pros and cons. Because if we only depend on measurement, which is expensive, if we depend only on modeling, it will induce a lot of uncertainties. So the idea is to combine both of them. Can we combine these 2 and bridge a hybrid system that will allow us more reliable MRV? The conceptual framework look like this. What really we have done was to deploy the sensors at different scales and collect the information in a near real time and feed that information to the models in near real time and then produce the output into the app. The app will be used by the farmers or the end users which they get the information and also provide the information. So this is the mechanism which we have created. So I will go into the details, but in a nutshell, the 3 scales, what we look at the plot scale, landscape level, and the regional scale. So plot scale, we are using a bunch of sensors, soil temperature, moisture, and the weather sensors in this. We deploy them in the field. And then landscape level, we are using the drones, but eddy covariance measurement, this is for the model calibration, but when we scale it up, we don't need these things. But fundamental is that we need the landscape level, plot level sensors we need to deploy. So data that is coming from this, we streamline the data flow. Now the data comes in a real time. So the data will be collected and processed and feed into the models. So the next one is at the national scale, we are using the Sentinel-1 and 2 data, which we connected to the Google engine, which will process in a real time. But we are using that information to track the management practices, not for the soil carbon. So we want to track whether the land is plowed or not, when it is planted, when it is harvested. These are the information we want. We are getting that from the satellite data. So that data works on each land parcel. So all this information will be integrated and then run the models and produce the output. I'll go into the details in the next. So in a nutshell, it works like this. When we go to any field, we have a baseline management, which they're already doing. They will be doing something, right? So we produce, and it is the app that will have an automatic land parcel detection. In the Scotland, at least, we have. When they go, they can click on the land parcel. That will be automatically identified and integrated all the databases in the background. I will show you how that works in the later on. And also, we created a soil sampling mechanism. Even though we know the soil stocks because it is integrated with the soil maps, but actually we designed a soil sampling mechanism where it will guide the farmers where to take the sample, and the sample is taken and analyzed, and that information is the basis for us to start the simulations. So we use the already existing information, and we take the samples and use that as a starting point. And then the sensors which are deployed continuously sending the information to our servers, and then actually the mobile app that will be used by the end users, the farmers, to produce the information and also collect the information. They submit the management information through that, whatever the management that is happening in the field. So I will come to that, how that happens. Then the simulations happens. At the simulations, we not only look at the best management practices, combinations that can sequester more carbon in that through the simulations. We suggest the farmers. We don't enforce them because we are not looking at the economic elements of it. So if the farmers choose certain management practice, we can track them through the real-time system again. So it's a continuously iterative real-time system. So this can generate, every data produced in this will be curated and kept in the server. So if you want use the evidence, this data could be used for an evidence for that purpose. Because every place we create a digital signature for this. That digital signature is very crucial to track the carbon. So the next part is, in a nutshell, how this works. These are the two farms we have put for demonstration. These are the both James Hutton farms. One is grassland site, another one is cropland site, crop rotations. The data, we deployed different sensors. That's a real-time dashboard of the the data that comes in. We connect with the models, and that is the app that takes in and produce the management data and reiterate. The models will run and produce this. So this is the Retina architecture altogether. I'm not going into the details, but if you want, we can chat later on. This is how entire thing drives. This will include the existing, all the databases in the background. So we use the LoRaWAN technology to connect with communicate with the sensors, because we find it to be cheaper, and in long run it is much cheaper for the farmers because they don't need to pay for it, for the communication element of it. So the sensors, we have a gateway. Gateway takes the servers and database it will enter into, then go into the Retina application. This is the data chain that we can see. So these are the models currently with us. We don't use a single model, and it will allow more models to come in. So currently we have 3 models, crop DNDC, ECHOS, and BASGRA models, which are already connected with the system. All 3 models run simultaneously with this data and produce the output. So what are the benefits of the Retina technology is to interactive real-time model predictions, and then complete data traceability, and data collection directly from the field without input from the farmers, which is very crucial. The farmer input have advantages and disadvantages. The disadvantage is it is prone to mistakes and also manipulation. So in order to avoid that, we take all the information from the sensors, and also we are automating even the farmer input from the management information in UK, because many farmers use the farm management software, like Muddy Boots and all. We write an API, we grab all the information. We don't ask any information to the farmer. So all come from automated systems. So this way, actually, we can rely on the systems. And also, real-time data visualization, informed decisions at the farm level. If they plow the land, when they come home, they know the impact of the greenhouse gas emissions or what is happening to their field for each land parcel level. I will show that. This is the app. I'll quickly show. It will take 2 minutes to cover this. So this is the layout of this. First, the farmers need to, it's having 3, I will stop here a bit. Oh, it's running, but you can pick the field. When you go, it will automatically, the GPS will identify the land. When they go into that is the land. You can click on the tab that will automatically identify the land boundaries, because we already incorporated this information in the background. So it will identify the land parcel. Each land parcel, they can give the name. What land parcel, if they don't need to put their entire farm into the system. They can put one land parcel to try. So that's what actually they can do. This is a soil map, soil distribution of this one, already integrated with this. They can see how the soil distribution around it. So, and also soil nitrogen, all the elements are integrated into it. So, but these are not accurate, but it just gives them an idea where they have a higher carbon as per the maps, soil maps. And later on, we asked them to take the samples. We developed an algorithm that is called the soil sampling algorithm, that smart algorithm, that will take the existing information to look at the heterogeneity of the soil and then develop the soil samples and ask them. Now you can see the soil samples will come in. And zoom in, come on. So that's the soil sample locations. So they can go into that, take the soil samples, and this will be precisely noted down, GPS locations we know, and also we record this information. So we know at each land parcel level where this is coming from. So, and then they can go to My Timelines. They can look at the management information. This is what they have done to this land parcel over a period of time. So though this is the only information we ask at this point, my activity, they need to submit this information with some level of evidence. What we do is, we need very few management practices, because in order to greenhouse gas emission and carbon, only few management practices that will impact, really. We don't ask for pesticide applications and all others at this point. So very few, they can select and submit with photograph associated with it. They just need a photograph, that's an evidence, and that is GPS located. So we know where that photograph is taken, what actually it contains, that is an evidence in the background. So these are the sensor locations where the sensor data comes in. So that gives a complete package altogether. So speed up. So these are the results at the end. That will show the results forecasting the yield. Still we are developing the visualization element of it, but that somehow look like our models will run up to 2050. That will project the trajectory, which direction they are in, the farmers are, if they manage the land in the same way. So I will stop here. I already know the scalability of the system. We need only 2 things, a bunch of sensors and an app. We don't need much more anything. So remaining all work done in the background. So in conclusion, Retina fulfills the functionality necessary for monitoring, reporting, and verification system to accelerate the efforts towards the net zero. And digital data that is collected across, when we scale it up, is highly valuable. We can use it for multiple purposes. We can harvest this data. And also, this approach will enable the data flow from the field to the end user in a real-time decision making. So thank you very much. Sorry, I'm over the time.
Yeah, okay, so thanks indeed, and I think that was a really brilliant example of one of the system developed along the lines of the kind of the overall system either Pete Smith or Keith Boshian had sort of planned or had this diagram. So really fascinating system that you developed. It really looks very impressive, really, how far you are in employing the digital technology. I think we will take one question here if somebody has over there, please. So now we have only this one microphone to the question first, and then if you can bring the microphone back.
Hi, I'm Eric Sechia, senior scientist at INRAE and developing some MRV approaches also. I have a question, which is if you want to apply such an approach at large scale, you mentioned that at some point you might be using remote sensing data or drone data. So what is your strategy for using that kind of data? Are you planning to do some data assimilation in the model, for instance, to constrain or better represent biomass spatial distribution or viability and how it impacts carbon stock changes?
Please wait for the mic so that also the online participants hear you.
We have already done the integration of the remote sensing data, which I haven't shown here because too much for 15 minutes presentation. So we have done that, but we are not using remote sensing for soil carbon analysis. We are using remote sensing for tracking the management practices, to validate the management practice, some of them. That's what our objective is. Because we are asking the farmers to take the real samples and analyze them for that. So there is no need for, again, doing it using the remote sensing, which is uncertain in my view. The other part you're asking about drones, yeah? Yeah, drones, we are using it for biomass estimation. That's what actually integrated into it. Because drones, why we want to use? For only biomass estimation, it's high intensity, because drones are very expensive to run and also analyze. So why we are doing it, the future objective is to biodiversity. Because we can, once we scan, we can also estimate the biodiversity in the field. So that is our objective. So it's not only for, it will add little value in terms of biomass estimations in our term, because the farmer knows biomass very well than this one. So because we are asking the farmer direct inputs here. So that's the issue. Thank you.
Yeah. Okay. Thank you very much. And one comment I would still like to make before we move on, and that is actually something that I should have asked also already for Pete to comment, is that, but also want to sort of bring this up here, is this kind of, you mentioned in the beginning of your presentation, like the need for harmonizing these very field-specific, spatially detailed systems with the national greenhouse gas inventory system. So I think that is something an important issue to keep in mind, and that is something that we will certainly address if not during this morning session, then in the afternoon session when we have the comments. But that is something that, thanks for bringing also this up, and thank you once again for this presentation. Thanks a lot. Yep, wow. Yes, and then the next presentation will be, we will hear and see that from a video that lasts for 17 minutes, I've heard. And that's given by the Jean-François Soussana from INRAE. And Jean-François is the vice president and especially responsible for the international polity matters in INRAE. So we will now hear and see the video that Jean-François has sent us beforehand.
Hello, I'm sorry that I could not join you, and I will be glad to offer a few comments during this meeting on how we can certify carbon removals by soil carbon sequestration in agriculture. Let me share my screen to show the presentation. So I hope we are set. Sorry for this. And yes, I would like to address this issue of certification of carbon removals by agricultural soil carbon sequestration. Let me say first that the voluntary carbon markets are indeed large in forestry, but very small in agriculture. We have prices on average around €13 per ton of CO2 equivalent, but prices can go, in fact, much higher in some specific projects. We know that to generate carbon credits, a project should be additional and measure the quantity in CO2 equivalents avoided and stored. So this means you have to account for nitrous oxide emissions or any other type of emissions, not only about soil carbon. You should guarantee the uniqueness of the carbon credits, and it enables the verification of the neat greenhouse gas mitigation in CO2 equivalents. And indeed, there are several business models that coexist with carbon offset projects led by international businesses or cooperatives or even technical institutes or regions. I will go back to the national labels after. And this is the sort of landscape we see internationally. It is with some certification labels that are delivered by some companies that operate standards. So there are names here showing some of these registries or companies. And we have also some national labels. In France, we have the Label National Bas Carbone. You have auditors, and you have also some consultants that intervene. And you see that, in fact, this landscape is already quite saturated with many program developers, marketplaces, retailers, buyers. And unfortunately, there are not really international standards about monitoring, reporting, and verification on soil carbon, which makes this process quite weak, in fact. So the European Commission has launched an action here on sustainable carbon cycles, saying that carbon farming should be developed to provide some carbon removals in the land sector, and with having every land managers that can access to verified emission and removal data by 2028. So this is an ambitious frame that the Commission is pushing forward. And in November, they had already some criteria about the way the carbon removals would be assessed, with criteria about quantification, additionality, long-term storage, and sustainability, meaning that not only should it be carbon storage, for instance, and therefore mitigation, but also contributing to adaptation, biodiversity, and other targets like water, circular economy. So these are the quality criteria that are being further developed. And as I mentioned, we have already in some countries some national labels like the Label Bas Carbone, which in fact are already quite similar in terms of looking at emission reductions that can be verified subsequently or upstream, also at indirect emission reductions, and possibly at the footprint of the emission reductions. So in this national label in France, both the methodologies and each project that rely on the methodologies are certified by an authority which is under for the Ministry for Environment. So the criteria are a bit similar. You have additionality, eligibility criteria. For instance, are the emissions reductions measured, the monitoring of the project, the assessment against the baseline, and obviously a certain scope is being defined. So the methodologies should be approved, and you see here how they are approved by the authority after a request for validation and after external reviewing. INRAE has been involved in that external reviewing, but there are also other experts. And projects should show their compliance with an approved methodologies. So they request also for labeling, and this can be investigated, and then it will be the authority that will label a project. So this is in a context where in France, we have shown from a study led by INRAE, that the carbon storage potential is quite big, around 30 million tons of CO2 equivalent, close to the aspirational 4 per thousand target. Most of that potential is in arable crops, with especially 3 practices: cover crops, grass lays, increased organic fertilization. And the costs are relatively high, but compatible, let's say, with the shadow price of carbon, around 55 euro per ton of CO2 in 2020. In that study, we could show that the potential is higher where the initial soil carbon stock is lower. So indeed, knowing the initial carbon stock is important for understanding the potential of carbon storage. So let me go back to those agreed methodologies, and especially one methodology that is for the croplands, where arguably there is the most potential for soil carbon. This methodology relies on the national study published by INRA at that time, showing the potential of practices like cover crops. And it is proposed to assess soil carbon sequestration against a reference scenario that can be based either on regional estimates or on farm-scale data, regional estimates of soil carbon or farm-scale data of initial soil carbon. There are discounts in case you use the regional estimates, but the discount is only 10%. And in case, which is also a risk, obviously, the carbon storing practices would be stopped after some years, the carbon credits would be discounted by 20% only. So arguably, this discount criteria are a bit weak, and I would like to explain why. So should we accept to use a regional estimate of the initial soil carbon stock? As I said, the initial soil carbon stock or carbon content is a strong driver of soil respiration and hence of soil carbon storage. If locally the soil carbon is already high, improved practices may fail to deliver carbon storage. One could argue that using regional means of soil carbon is risky, first of all because means are quite difficult to establish given the large variability in soil carbon and in agricultural practices. Large variability in soil types also, and moreover, because the relationship between carbon storage and initial soil carbon stock is nonlinear. So in case you want to use a regional mean, you should really have some work to establish what the mean is, what the average is, by use of databases, for instance, of the agricultural soil analysis, of remote sensing of bare soils, of near-infrared spectrometry. These are possibilities to improve your baseline estimate of the soil carbon stock at regional scale. I will go back to novel technologies with neutrons that could be used, and verification will be needed after some years. So if you use a regional mean, you need also to randomly sample some locations and show there has been, to verify there has been some increase in soil carbon. This is also true at the farm scale. You will need to verify. So this is a new technology that is being used in the US and Canada, which has potential because it is a direct measurement of soil carbon at 30 centimeter depth. It can scan 1.5 meter wide. It progresses at a speed that could be up to 5 kilometers per hour. That's quite moderate, one could say, but then it could scan a field and show the change after some years in the neutron scattering scanning, and therefore it is correlated to the soil carbon stock, and therefore you could use it to have a profile of the changes in the soil carbon stock. So here again, there are some emerging technologies that could be used. So we could improve, in fact, the verification, and we could improve certainly the estimates of the initial soil carbon. Let me come to another drawback, which is linked to the reversibility of the practices and of the soil carbon stocks. What happens when you stop the improved practices is that you have a fast out phase. Carbon goes out quickly from the soil. And if you want to go back to the initial equilibrium, you have to build up rather slowly, in fact, your carbon. So the risks are quite high that if you stop your improved practices, you will lose quite a lot. And let me go back to the implications of using a global warming potential of 100 for the carbon credits from carbon storage in soils. Well, actually, if the additional organic carbon stored in soils is released before 100 years, the impacts on climate will be less than expected from the use of this global warming potential that assumes a 100 years horizon. So the long-term monitoring of agricultural areas benefiting from carbon credits should be pursued. I think that's a commitment we should take. And we will see that it could be done with remote sensing. And moreover, the carbon credits may need to be attached to a land piece rather than to a farmer, because no farmer can obviously contract over 100 years. But one could say, if you have been paying for increasing soil carbon on a certain piece of land, well, the improved practices should stay there over several decades and, if possible, 100 years. Now we have another problem, is that with climate change, the soil organic carbon content is likely to go down in some regions of Europe by the end of the century. The baseline of soil carbon will be affected, and possibly new practices will be required. Some better adapted crops may need to be used rather than initial crops. So you see, we are in a dynamic environment here with climate change, and we need to think how we can maintain improved practices, but not necessarily the same as initially, actually practices that may be better adapted to climate change, and this to sustain the soil carbon increase. So we have been indeed thinking in the scientific community about a framework for monitoring, reporting, and verifying the soil organic carbon stock change. And this is a paper that summarizes this sort of a framework. It may seem a bit complex, but it's really how can you calibrate and validate soil organic carbon models and greenhouse gas emission models with both the long-term field experiments, with the short-term carbon flux experiments, where you have flux towers, for instance, and how you can constrain the models with remote sensing to verify the farm activity data and provide inputs to run the models. And you can monitor both the vegetation cover and the soils when they are bare. So you need indeed to have a verification, and that can be done by resampling or monitoring, as we have seen with the neutron scattering example, the areas where you have, and you need ground truthing for this, where you have a soil organic carbon stock change. So combining these different methods actually can lead you to rather a robust and relatively accurate estimate of soil organic carbon change over time. So this is already happening, and this is an example where the soil carbon modeling is constrained by remote sensing of the vegetation cover and by the soil carbon data, plus, when possible, the farm activity data, to provide a scalable estimate of soil carbon stock change from the field scale up to the country scale, as you see here for Netherlands. And the same for France here, where calculations of annual net CO2 flux can be done with the Sentinel satellites at 10-meter resolution for croplands. So the point is that we should monitor the areas where we have carbon credits involved to make sure that the activities, for instance, the cover crops, are there. We can monitor it with satellites. And moreover, by monitoring the vegetation cover, monitoring the bare soils, we can indeed improve the modeling and improve the quality of the estimates that will lead to those carbon credits. So I think that's an important development we should pursue. And this is the kind of framework we would like to build through an international research consortium on soil carbon. This has been supported by European Commission through the Cercasa project. You see the vision of that project, of this consortium, bringing research, private sector, public agencies, and building especially this monitoring, reporting, verification, but also, that's pillar 2, bringing some other changes like linking farmers with innovation and enabling environmental and knowledge co-creation. And this is really an important step that we would like to see to support the 4 per thousand initiative. So I think I would like to stop there and to have just a few concluding comments. We now have methods that are quite reliable for carbon stock assessment involving data, remote sensing modeling. By the way, you could also have those similar methods for tree biomass. We are suffering, I think, from rather unstandardized methods that are often quite costly for certification of carbon removals by soil carbon storage. International standards are needed, and that's why an international research consortium is needed. We think that regional or national authorities could play a significant role in facilitating those methods and therefore the access to carbon credits at a lower cost. And we should think also that we would try to compensate farmers that have already achieved high levels of soil carbon. By the way, this could be done by use of remote sensing because you could prove that they have been doing, for instance, cover crops or grass leaves quite early on. This is accessible in some of the stored images. And we think, I hope these comments will be useful to your conversation during the meeting and that we can improve the methodologies and therefore further develop carbon farming and soil carbon storage, which is certainly an important option for the future, both for climate mitigation, adaptation, and food security. Thank you.
Yes, I think this Jean-François' presentation, I think it fitted very nicely to the overall picture, but still it brought like additional insights to the system. So that is, I don't think that we will even, I will even allow a comment here. I think we will, if you have some thoughts in mind, please bring those to the discussion we will have in the afternoon. We have a little bit more time to discuss in the afternoon. And so we'll move on to the fourth presentation of this morning, and we will end this session by before 12:45, so we will be 15 minutes late. We started 10 minutes late, but so we will be finished by 12:45. But the fourth presentation we'll hear, so that will be Istem Fer from Finnish Meteorological Institute giving that presentation. Istem is a senior research scientist with us, and Istem will tell you about the carbon measuring, reporting, and verification system that we are developing at FMI in our research group. So, yeah, without further ado, so Istem, you're welcome, and the floor is yours. And you have like the 15 minutes for the presentation and then 5 minutes for the questions. So yeah, all right, go ahead, Istem.
Thanks. Thank you very much. Hello, everyone. In this talk, I will be presenting another MRV system example. I'm kind of lucky to be the last talk in the session because the previous talks already gave a brilliant introduction to the topic, so I don't have to do that much. But I will still try to clarify where we are operating with our MRV approach at FMI. So we have two main focuses. One is more scientific, towards more method development, and what this talk is more about. How can we improve our models? How can we improve the measurements, the algorithms that combines the models and the data? And then we also have this more service providing focus where we are trying to work towards providing carbon estimates and decision support. Here I tried to summarize that on the spectrum from simpler, more superficial carbon calculations to more complex and resource-intensive approaches. We are operating more towards this complex side of things. We heavily deploy process-based agro-ecosystem models, and we are focusing on providing local model simulations synthesized with site-level informations. This slide was just to say that we mainly work on the plot scale to regional scale in our approaches. So At FMI, we also rely on many different process-based models because we would like to be able to carry out these calculations for many different ecosystems and different management options. And as you might well know, different ecosystem models have different strengths and they encompass different process representations. So you need this ability to switch between models as you are switching between simulating different ecosystems. And it's also maybe worth noting here that even two models can simulate the same setting as well. It's still worth simulating the same setting with more than one model because you can still gain additional insights from these different hypotheses that are encompassed in these different models. So when I show this slide, people usually ask me, where is Yasso? And for those who don't know Yasso, Yasso is the soil model that is being developed in Finnish Meteorological Institute, FMI, created by Jari Liski et al. And since its creation, it has been used in many different Earth system modeling studies, greenhouse gas inventories, as well as land use change and climate change research. It is under development continuously, and the latest version has been published last year, and we use Yasso quite a lot in our group as on its own, but we also replace the soil modules of these other models that we have with Yasso. For example, the nitrogen version of Yasso that has been recently developed in our group by Julius Vira has been coupled to this bus graph, another vegetation model. And similarly, we also in-house have our own simple vegetation model development, and the efforts are led by Hui Tang in our group, and Yasso is also the soil module there. So the ability to work with these, or the need for working with multiple models is needed, but it's also very challenging because all of these different models lack standards around the way of their operations. So they require different inputs, they have different input formats. So just think of all the challenges of working with just one model and multiply it. If there were some, for example, standards around the way of their operation, this multi-model system could scale much more easily. And the other challenge is that these models are heavily parameterized. They require a lot of data to initialize them, to calibrate them, if not just to drive them forward. They are very data hungry and data dependent. So in order to bring this whole multi-model and model operation and model data integration to a much more efficient and scalable level, we are running our models through a cyber infrastructure tool called PCAN, which stands for Predictive Ecosystem Analyzer. You saw the mention of that already on Jagadeesh's slides. Just to give a summary, PCAN itself is not another model, but is this informatics system that wraps around the models and takes control of the data flow in and out of these models. It also standardizes and automates the analyses that you typically do with these models. In our group, we use PCAN a lot and develop PCAN a lot, and these days our focus is mostly pushing it all to more lightweight and containerized computing systems to make this more scalable. So happy to talk about PCAN if you're interested later. Then what about data? We, of course, have direct measurements from the fields. For example, this nice data set compiled by Tuomas Mattila et al. Is one example. And the other one that I want to highlight here, that if you haven't heard in this conference already, there's this new methodology that has been developed by Tampere University in collaboration with others. It's called soil carbon measurement based on laser-induced breakdown spectroscopy, LIBS for short. With this method, you can already obtain results in the field, and tomorrow at Quidia there will be a demonstration. I think there was a demonstration as well there. So if you're curious about details, please go see the poster by the Tampere University there. We also have automated pipelines, of course, the usual suspects, retrieving data from meteorological stations, on-farm sensors, eddy-covariance towers, etc. And we also have an application to collect field activity data from farmers, albeit this requires manual input. So farmers or a field operator would still need to fill out some events through this user interface. And this app under the hood translates these events into a standard file format, which we then feed into our modeling and also data visualization workflows. So on the right there, you are seeing these events being displayed as per collected by this app. And this graph is from Field Observatory, which is our dissemination channel. It's an online web service, which is alive. You can go visit fieldobservatory.org and see similar figures from all our benchmark sites. So we distribute all our modeled and observed data through Field Observatory. Another point I would like to make about data is that it's not over once you just fetch the data. You still need to process it a lot. For example, to derive the variables of interest, such as leaf area index from satellite images. Another one that I want to highlight here is this gap filling algorithm that we often heavily rely on. Flux data, as you might well know, is one of the most important data types that provides us some direct measurements in the fields about the carbon balance of the fields. But it's a tricky data to work with because it requires filtering, it requires quality control, it requires gap filling to obtain a more complete picture of what's going on in the field in terms of carbon balance. And also, if you want to use that data to calibrate your model or compare with your model outputs, you still need to aggregate these momentary flux values to their daily values because that's the time step that most of our agroecosystem models run at. So indeed, all of these kind of point to that the quality of the gap filling algorithm that you use has a profound impact on your model calibrations and also the overall carbon verification methodology. And one of the most commonly used gap filling algorithms called MDS has been recently shown to introduce, for example, significant biases, especially in the northern latitudes here on the left column. The darker the colors, the bigger the bias. But in our group, we have recently developed another machine learning based gap filling algorithm called extreme gradient boosting, and it significantly reduces those biases that are introduced during the gap filling processing. So if you're more interested in the details, please see the paper by Henrika Vekuri. And this is the algorithm that we use now in our system. So if you're feeling a bit lost about how all these different components are coming together, this is just a summary slide. So we have these different multi-stream data pipelines flowing into our servers. Big data, small data, automated data, manual data, they all come to our servers where we are running these data processing algorithms and where we are also running our models through this pecan tool. And then we disseminate all the modeled and observed data through Field Observatory. And as I mentioned, some of these components are now being replaced with a more modern and scalable OpenShift container platform to make it more accessible to third parties. If you're interested in more details, please go see the Field Observatory poster that we have here. So just to come back, in the remaining minutes of my talk, I will mostly focus on this black box in the middle where we are running our model data integration and give some examples of what we are doing. So we are, of course, trying to understand the driving sources of uncertainty in our agroecosystem models, and we are trying to identify the data needs to constrain those. We calibrate and recalibrate our models at our benchmark sites, test fields. We use Bayesian calibration to reduce the uncertainties around our model predictions and also improve their accuracies. We use data assimilation. We assimilate data to inform model states and improve them. For example, in this one study, one of the key takeaways was that already including the first few measurements, like say 5 to 15 years of soil organic carbon measurements, impacts the state enough to reduce the error in decays log like 50 to 60 years projections. So that's a very useful method. Using similar methods, we are also putting our models into forecast analysis cycles. So I will just break down this long title into smaller bits. So with our agroecosystem models, we make a 15-day forecast into the future. Here near term is 15 days because that's the that is what is provided by the European Centre of Medium-Range Weather Forecasts, which we use to drive our models with. Then in near real time, meaning every day we go get the observations from yesterday, be it the carbon flux, be it the leaf-area index if there was a satellite image available. Then we adjust the model states with these observations. And from those adjusted states, we make another 15-day ecological forecast into the future. And we do this every day in an operational manner, similar to what weather forecasting is doing. With this, we aim an ultimate out-of-sample testing for our model predictions. Also, you can, for example, plan your field visits more strategically, knowing the next 15 days for collecting samples, for making observations, for example. But we also would like to provide some decision support with this. Given the next 15 days, can we optimize some of the field activities, such as the amount and timing of the harvest, fertilization, application, irrigation, and so on? And more importantly, what is the impact of these short-term interventions in the longer-term carbon balance of the field? So we are currently archiving these near-term forecasts to be able to analyze those retrospectively in the future. And then our what-if scenarios are also including synthetic data experiments, meaning that we are generating some pseudo-data observations, then we assimilate them into our models to see their impact on our projections and our overall statistical inferences. These kinds of observing system simulation experiments provide us with research priorities and development priorities. Then we are, of course, also trying to replicate the findings that are going on in our benchmark sites. These benchmark sites usually typically have this one control plot where business as usual management scenario is ongoing, and then there's next to it an experimental plot where one of these carbon farming practices are being tested. So with our models, we are trying to replicate these findings as well. Tomorrow, I believe, some of you will be visiting two of our benchmark sites, Wiki and Quidia. But data is kind of, so to speak, giving you the one side of the story. When you observe something, you don't know whether it's due to the management activity that you just introduced, or is it due to the weather event that year, or is it due to interaction between those two? So in order to disentangle these kinds of things, we use our models. Here, for example, again, Jari Liski in our group tested the impact of weather variability in the carbon dynamics within the year. So he replaced systematically the observed variables with meteorological drivers, one at a time, with the climatological average, and simulated the net ecosystem exchange with one of our agroecosystem models. And it looks like, indeed, the carbon dynamics within the year is quite sensitive to weather events, especially the precipitation amount and the timing of the precipitation. So much so that maybe the management action that you took that year is overwhelmed by what the weather is like during that year, or if not heavily modulated by the weather events. So, but this is all in progress, and all the more reason to continue modeling and simulating these fields. So maybe with that, I will stop here, and I would like to thank our collaborators and funders, and I will just leave this slide, to get some questions. Yes, yeah, thank you.
Thank you very much, Istem, for presenting our work. So excellent presentation. Thank you very much. So any questions to Istem? Please go ahead.
Thank you. What data do you actually collect at these sites that you have? And is it the same? So you have 100 farms that you have business as usual and carbon farming practices on? So what data do you collect and how do you use it to improve the models?
Yeah, that's a good question. So we have different tiers of...
I wonder if your microphone is that headset is on, so we'll be fine. Yeah.
Okay.
Okay, go ahead.
Okay.
Sorry.
We have different tiers of sites. There's this 100 sites that are applying these experiments, control and experiment fields. We have 20 more intensive sites. From those generic 100 sites, we are only currently collecting data like yield, meteorological drivers, leaf area index. That's what we are monitoring. But we have 20 more intensive sites from which we are also collecting soil samples. We have collected soil samples in the beginning of the experiments. And now this year, 5 years later, after the beginning, we are again going to collect the soil samples from all these sites.
Yeah. I think we have time for one more question, so please go ahead.
Hello, Blaine Lees, Senior Data Scientist from Agreena here. A quick question. On your satellite-derived LAI, are you using the Sentinel product or are you using the bands to develop a model to estimate the LAI?
Could you repeat the...
For your satellite-derived LAI, are you using the product provided by Sentinel, Sentinel-2, or are you developing a model based off of the bands?
Yeah, we are retrieving the Sentinel-2 images either from Google Earth Engine, GE, or Amazon services. And then on top of it, we use the SNAP algorithm to derive the leaf area index.
Thank you.
Okay, thank you once again, Istem. Thank you. So we've heard 4 really carefully planned presentation and excellent talks, and I think they gave a very nice overview of the status and future directions of these measurement reporting and verification systems, and I think they serve as an excellent basis for the afternoon discussions and the comments where we will have 6 I would say stakeholders who are somehow related to this or for whom these MRV estimates are relevant. We will hear their comments, and we will have then also time to discuss about those various viewpoints. So with these words, I'll thank everybody once again, those who presented, those who asked, and those who listened. Thank you very much for coming to this session. And we will continue this theme at 1:00 in this room with these 6 comments and time for questions. So you're very welcome to join the afternoon session as well. Thanks you once again. The session is closed.